Okay, so in this class, we're going to learn about absolute and conditional convergence, and we're going to see our last two convergence tests for the semester. So let's write out the first 5 terms of this series. It's the sum from n equals 1 to infinity of -1 to the n plus 1 over n. So my first term you get by plugging in n equals 1. So if you plug in n equals 1, you replace the n with a 1, that exponent becomes a 2. 1 plus 1 is 2. And what is -1 squared? 1. So this is 1 over 1, which is 1. Plug in n equals 1 and you get 1. All right, now I'm going to plug in n equals 2. So if you plug in n equals 2, the denominator is 2, right? And the exponent is going to be 2 plus 1, which is 3. And -1 cubed is -1. So there's a 1, but this is negative because of the negative sign. All right, now I'm going to plug in n equals 3. So my denominator is going to be a 3. Replace that n with a 3. And my numerator is going to be -1 to the 3 plus 1, which is 4. -1 to the 4th is +1. So we're going to have 1 positive this time. Plug in n equals 4. So replace the n in the denominator with a 4. And then you're going to have -1 to the 5th, which is -1. -1. And one more term. My denominator is going to be a 5 when I replace that n with a 5. And this is going to be -1 to the 6th, which is +1. So that's the first 5 terms of my series. This is an example of an alternating series. It's called alternating because of the alternating signs, positive, negative, etc. Okay, we already know that the harmonic series, the sum from n equals 1 to infinity of 1 over n, without the alternating signs, diverges. But let's think about the alternating harmonic series. Okay, so now I'm going to alternate the signs. It's the harmonic series, but alternating the signs. So I'm going to stand at one wall here. Pretend that this is n equals 0. This is 0 on a number line, and that wall is going to be 1 on a number line. And I'm just going to follow the terms here. So I'm at 0, and I'm going to add 1, because the first term is +1. So I'm going to walk across the room to +1. Okay, now I'm going to subtract a half. So I'm going to go left a half. Make sense? Okay, so left a half. Now I have to add a third, which means I need to go right a third. So I need to go, yeah, third of the way to the right. Okay, now I need to go left a fourth. And then right a fifth. Do you think, am I converging in on a single location on the number line? Yeah, and it's not very far from me. I've gone 5 terms, and the next term I need to go a 6th, and then a 7th, and I'm going to be converging in on the sum of this alternating series. Okay, so we're going to we think it converges, and we will confirm that with something called the alternating series test. Okay, it says that if you have an alternating series, so the terms go positive, negative, or negative, positive, just has to alternate. If the terms of the series are decreasing and the limit as n goes to infinity of the terms is 0, then the series converges. So the rationale is captured in the diagram and in the walking back and forth demo we just did. So if you start with the first term, you go all the way over, and then you subtract the next term, add the third term, subtract the fourth term. You're sort of converging in on some sum, the final sum of the infinite series. When you're writing a proof that uses this test to prove convergence, it's enough to just write a sentence that says we have an alternating series whose terms and absolute value are decreasing towards 0. Thus, the series converges by the alternating series test. So this is the alternating harmonic series. To prove that it converges, all we have to say is the terms in absolute value, meaning the terms are a sub n, which is 1 over n, right? The terms just look like 1 over n, are decreasing towards 0. So the series converges by the alternating series test, AST for short. So the terms are decreasing, getting smaller and smaller and smaller, and they're heading towards 0, as opposed to decreasing towards negative infinity, right? So they have to be always decreasing, and the limit has to be 0. All right, let's look at another one. So this is an alternating series, because that negative 1 to the n is going to make the signs alternate. So I'm going to write out the first 5 terms. So if I plug in n equals 1, negative 1 to the first is going to be negative 1, so this is going to be negative, and then 1 over 2. When I plug in n equals 2, my negative 1 to the n is going to become positive. Negative 1 squared is positive. I'm plugging in 2, so this is 2/3. My next term is going to be negative, because negative 1 cubed is negative, and I get 3/4. And then I'm going to have plus 4/5 minus 5/6 plus da, da, da. Are these terms decreasing in value? No. Are they approaching 0? No. So the alternating series test does not apply. What test does apply? No. The test for divergence. If the terms don't approach 0, the sum diverges, right? What limit are these terms approaching? 1. Yeah. So the limit as n goes to infinity of the absolute value of the terms is 1, not 0. It doesn't really matter what it is. It's just not 0, right? Which tells us that the sum diverges. So the sum diverges by the test for divergence. So you always want to check that first, right? If you can say the terms don't go to 0, it diverges, that's like the easiest test. And you don't have to do a whole lot of work to try to prove convergence or divergence. Okay, so for alternating series that satisfy the conditions of the alternating series test, namely that the sequence is decreasing for all n and that the limit is 0, there is an easy formula to figure out the error of cutting off the series after n terms versus looking at the sum of all infinitely many terms of the series. So it's just the next term in the list that's missing. So if we did our thing with walking from 0 to 1, so if I start here at 0 and my first term is 1, walk all the way over here. Then I subtract a half, end up in the middle. Then I have to go that way by a third of the distance. Then I have to go a quarter of the distance that way. And then a fifth that way, right? So right now I am very close to the actual sum. And if I go that way, I'm going to jump over it, right? So if I stop adding right now, the error is less than the next term because my next term is going to jump me right over the sum. So the error, if you approximate by the first n terms, the error is at most the next term It's always going to be less than whatever the next term is. So if I want to find the error in approximating the alternating harmonic series with the first 9 terms, it's just less than the 10th term. So I would say the sum from n equals 1 to infinity of -1 to the n plus 1 over n can be approximated by just doing the first 9 terms of the series, which would be the sum from n equals 1 to 9 of -1 to the n plus 1 over n. And my error would always be less than or equal to the 10th term in the series, the next term after I have truncated. So my next term, if I plug in a 10, I would have -1 to the 10 plus 1 is 11 over 11, over 10, sorry. And it should be an absolute value. It would be less than. Yes, it would be less than, but it's still true that it's less than or equal to. I tend to write the or equal to, even though it's superfluous. So it turns out that my error would be less than a 10th. So we're not going to do the calculator bit here. Okay, so here's another one. Actually, I'm going to skip number 7. Save a little time here. Talk about it in number 8. All right, it's easy to prove convergence using the alternating series test. All you have to do is write that sentence. The terms are decreasing towards 0 and the signs are alternating, so it converges. But if you already know that the non-alternating version of your series converges, it only makes sense that if some of the terms are now negative, the sum would be smaller. Smaller than a finite number is still finite, right? So if you take a convergent series and make some of the terms negative, it will still be convergent. So this is called the absolute convergence test. It says if the sum of the absolute value of the terms converges, then the sum where some of the terms might be negative also converges. So if I look at the sum of the alternating 1 over n squared series, I know that 1 over n squared converges. I already know that. So I know that the sum of 1 over n squared, which is the same thing as the sum of the absolute value of my series, converges. So by the absolute convergence test, the alternating version must also converge. Okay, a little more vocabulary. If the sum of the absolute value of the terms converges, which means that the alternating version or a version where some terms are negative also converges, then we say that the sum of a sub n is an absolutely convergent series. It converges as is, and its absolute value sum converges. So we call it absolutely convergent. If the absolute value of the sum diverges, but the sum where the signs are alternating converges, then we say that the alternating sum is conditionally convergent. So it converges, but its absolute value does not. All right, so let's look at these two series that we've talked about today. They're both alternating. We've got the alternating harmonic series, which we decided converges. But we know that the harmonic series, where the signs are all positive, diverges. And then we have the 1 over n squared, alternating version and positive version. We know they both converge. So to write this all out really explicitly, the sum of 1 over n diverges, but the alternating version of the harmonic series, negative 1 to the n plus 1 over n, converges. So we call this alternating version the sum of negative 1 to the n plus 1 over n is conditionally convergent. It converges, but its absolute value does not. So we call that conditionally convergent. And then for the 1 over n squared version, we'll say the sum of 1 over n squared converges, and I should say, and thus the alternating version has to also converge by the absolute convergence test. The alternating version also converges. So the alternating version is called absolutely convergent. Because it converges and so does its absolute value. So if a series converges and so does its absolute value, we call it absolutely convergent. If a series converges but its absolute value does not, we call it conditionally convergent. Okay, here's a crazy thing about infinite series. If you regroup the terms in a finite series, the sum is unchanged, right? The addition is commutative. You can do it in any order you want. Commutative and associative. So if I just add these left to right, 1 minus 2 is negative 1, plus 3 is 2, minus 4 is negative 2, plus 5 is 3. True? Okay, if I regroup them, let's see, 1 plus 3 is 4, plus 5 minus 2 is 3, and then minus 4. 4 plus 3 is 7, minus 4 is 3. Still 3. Obviously, right? You can do addition in any order you want. But if you regroup the terms in an absolutely convergent series, the sum remains unchanged. So if it's absolutely convergent, that same rule holds. You can rearrange the order of the addition. But mysteriously, this is not true for a conditionally convergent series. So if some of your terms are positive and some are negative, you can't rearrange the terms. You get different sums. So let's look at the alternating harmonic series. 1 over 1, minus a half, plus a third, minus a fourth, plus a fifth, etc. Okay. So if I group them with some parentheses, I do that first, and then the negative 1/4, I'm going to switch places with the 1/3, and then I'm going to put the 1/3 and the 1/6 together, and the 5th and the 10th together. Does everybody see the pattern of how I've regrouped these? So I'm keeping out multiples of 4. All right. So 1 minus a half is a half. Then I have minus a fourth. And then a third minus a sixth is a sixth. And then there's the 8th. Right? And then a 5th minus a 10th is a 10th, etc. Okay. So now all my denominators are multiples of 2. So if I factor out a 1/2, I get 1/2 times 1 minus a half plus a third minus a fourth. And this was my original series. So the sum of the original infinite series is equal to half of itself. That's impossible, right? Because we know it's finite. We know it's a finite number. If it were infinite, it could be half of itself because half of infinity is still infinity. But we know this converges to some finite number. And if you regroup the terms, you get a half of that finite number, which is really weird, right? It turns out that if you suitably rearrange the terms, you can make any conditionally convergent series sum to any real number you want if you regroup it in an appropriate way. It's just hard to think about. Weird. There won't be anything about that like on a test or anything. I just thought it was a cool thing to show you. All right, so that is it for the demo. Try some of the activities.